Hello friends, this is Animesh and welcome to the Get Mantra. So in the last video we have seen about the working of the enhancement type and Mosfet. We have seen the different cases in this. First we have seen that when we are going to make the VG or ground voltage equal to 0 and the drain voltage equal to 0, then what's happened now? What we are doing, we are still making the gate to source voltage or get voltage to 0 volt, and we are applying the drain to source voltage here, right? So here we are applying the drain to source voltage. So on increasing drain to source voltage, we have seen only the depletion region width at the drain is increasing, because this diode is in reverse bias, right? Now we have seen our third cases in which we are increasing the VGS. We are increasing the VGS and we are making the VDS equal to 0. Now in this process, when we are increasing the VDS, the more and the more electron from the bulb, from the source and from the drain are coming to the near the SiO2 interface, near the SiO2 interface, and hence when this voltage VGS is greater than a particular voltage, this is called the threshold voltage, the inversion layer is formed here, and we can say that the channel is created here. The channel is created. So what is the threshold voltage? The threshold voltage is the voltage at which the channel is formed here. Channel is formed between the drain and the source, or between the source and the drain, right? Now we have seen that what's happened when we are increasing the VDS by a small amount. The first we are making the VGS is greater than VT naught, that is threshold voltage, and we are increasing the VDS. Then we have seen that the channel current is flow. The channel current is flowing, right? And we have also seen that this channel current is the function of both the gate to source voltage and the drain to source voltage, right? And we have also seen that at the constant VGS, this I, the channel current, or we can say the drain current, is proportional to the drain to source voltage, right? Now we have seen this graph, this waveform between the ID and the VDS, and we have seen that how it's working as a linear region. Now we have seen what happened when we are increasing the VDS, that is the drain to source voltage, by a large amount. Then we have seen that on increasing the drain to source voltage, the voltage difference between the gate and channel is decreases as we are moving from source to drain. So at source in the voltage is VGS, and at drain in the voltage is VGD, that is the VGS minus VDS, right? And as long as this voltage VGD is greater than the VT naught, only the shape of the channel, is tapered. The channel become tapered, the channel become tapered, right? And the resistance of the channel is getting increases. Resistance of the channel is getting increases. Due to this, the conductivity of the channel is decreases, and hence there is a bend in the ID/VDS curve, right? And when at the VGD equal to VT naught, or we can say that the VGS minus VDS equal to VT naught, and the channel is pinch off at the drain end, and this voltage is known as the VD set. And theoretically, when we are increasing the VDS beyond the VD set, the shape of the channel are not changing, and a constant current is flow through the channel, and hence we can say that this channel is in this MOSFET is in saturation region, right? When the VDS is greater than VD set. And we have seen this, this all things, and we have seen how the MOSFET is working in the cutoff region, in the linear region, and in the saturation region. and we have also seen that the current equation for the n channel MOSFET and as well as the p channel MOSFET, right? Now after that we have seen what happened practically when the drain to source voltage is greater than the VD set. Okay, so we have seen that when the VDS is greater than the VD set, okay, the shape of the channel practically is not same, okay, is not same, and the pinch off point that occur at the drain end is moving now toward the source end, okay. Because of that, the effective channel length, this we can say that this is the L effective, this must the L effective, okay, this must the L effective. The effective channel length is decreasing, okay, this effective channel length is decreasing, and the depletion region, okay, and the depletion region near the drain, okay, is increasing. Because of that, when the electron is moving, okay, when the electron is moving from here to here, okay, since the voltage across the channel is constant equal to the VD set, right, and the equal to the VD set, and hence and the excess voltage, right, and the excess voltage that is beyond the VD set is present across the depletion region here. So when the electron is moving from the source, okay, and it's reached to the channel end, then due to the large voltage, okay, beyond this depletion region, okay, the electron that present here at the channel end experience a large electric field, okay, a huge electric field, and due to this, it's because of the large electric field, okay, that is applied by the excess VDS, which is equal to the VDS minus VD set, okay, in this depletion region, it accelerate and reach to the drain end, okay. So when the electron is coming from the source end at the channel in, okay, from the source end at the channel in, okay, and beyond this channel, okay, in the depletion region, it's experience a large electric field, and due to that large electric field, it gets accelerated in the depletion region and it's reached to the drain in, right. And we have seen what happened here, okay, this is the L effective length of the channel, and we have seen, okay, the voltage across the channel is constant, that will be equal to the VD set, right, that will be equal to the VD set here, and that will be equal to the VD set, right, and the excess voltage is appear across the depletion region, that is equal to the VDS minus VD set, right. And we have also derived the equation, the current equation, okay, and the drain to source equation for this channel length modulation, and we have find that the drain to source current in the due to the channel length modulation is not only depend upon the gate to source voltage, it's also depend upon the drain to source voltage. Now we have seen that this drain to source current in the saturation region, because of the channel length modulation, is the function of the gate to source voltage and drain to source voltage, and due to the decreasing of the effective length of the channel, the drain current is increasing, okay, increasing in the channel in the saturation region. Earlier, without channel length modulation, the drain current is constant or it's saturated in the saturation region, but because of the channel length modulation, the drain current is increasing, okay, it increasing in the saturation region. And now when we extend this, okay, plot, okay, it will cut at a point on the VDS axis at a point, and that point is called as the early voltage, and that will be equal to the 1 by lambda, where lambda is equal to process technology parameter, okay, and its dimension is volt inverse, right. Now after seeing this, Now we will see what will be the resistance, drain to source resistance in the linear region and as well as in the saturation region, right? Okay, so let's see here. Now we are going to see the resistance, in the linear region as well as in the saturation region. So we know that, we know that uh, let's see here from here. In the linear region or in the triode region or in the ohmic region, we know that the drain current is the drain current in the linear region is in linear region or in the triode region, as we know that the drain current equation is IDS, is mu n COX W by L, VGS minus VT naught, and here VDS minus VDS square divided by 2, right? So for the very small value of very small value of VDS, that is VDS is less than 15 millivolt, we have seen in the graph. So due to this very small value of the VDS, we can neglect this VDS square term, because if the VDS is small, then the VDS square is also very small, and hence our new current equation will be like this: mu n COX W by L, and here VGS minus VT naught into VDS, right? And then we are going to differentiate this equation, did this equation with VDS. So we will find nu n COX W by L, and this VGS minus VT. Now when we take the reciprocal of this, that is the RDS will be equal to the dVDS divided by dID will be equal to the 1 divided by slope of ID VDS curve will be equal to the 1 divided by nu n COX W by L and the VGS minus VT, and here this is nothing but the drain to source resistance, in the linear region, because here we are using the linear current. So what is this? This is nothing but the drain to source resistance, in linear region. The resistance, drain to source resistance in linear region, right? In linear region, and we have seen here this RDS, is inversely proportional to this VGS, right? And we have also seen that as we are increasing the VGS, the resistance of the channel is decreases, and hence the conductivity of the channel is increases for the very small amount of the drain to source voltage in the linear region, right? So this is the drain to source resistance in the linear region. Now we are going to see the resistance in the saturation region, right? So in saturation region, as we know, the drain current equation IDS will be equal to the 1 by 2 UN COX W by L VGS minus VT naught whole square into 1 plus lambda VDS. Now we are we are differentiating this IDS with respect to VDS. Okay, and now we can say this is the 1 by 2, okay, into nu COX W by L. Okay, now this is the VGS minus VT naught whole square. This is 1 will be equal to 0 and plus lambda. Okay, because this is the constant, differentiation of the any constant will be equal to 0, and this is with respect to VDS, and hence it will be the lambda. Now see here, for this, what is this? This is the drain to source current without the channel length modulation. This is drain to source current without channel length modulation. Okay, and what is this? This is the did upon me dVds. This will be equal to 1 upon me R ds, drain to source resistance. Okay, and hence it will be equal to id, this is the without channel length modulation, into lambda. Okay, into lambda. So here rds will be equal to 1 upon my lambda. This rds, okay, this drain to source resistance in the saturation region, okay, in the saturation region is called as the AC resistance. Okay, this is called as the AC resistance, or we can say this is the incremental resistance. It will be denoted as R naught. Okay, R naught. So we have seen here the R naught will be equal to the, okay, we can also say that this output resistance will be equal to the 1 divided by lambda, and this ID will be equal, it will be without channel length modulation. So we have seen the resistance in both the linear as well as in the saturation region, right? Okay, so in the linear region, the resistance will be equal to the 1 upon mu n COX W by L VGS minus VT naught, and in the saturation region, the R naught will be equal to the 1 upon mu lambda ID. If now we can say here, if, okay, if lambda is equal to 0 means no channel length modulation. For the no channel length modulation, this R naught will be equal to the infinite, right? Generally this R naught will be high. So we have seen the resistance in the linear region as well as in the saturation region, right? Now we will see, okay, this is the current equation for the p channel MOSFET or the n-type MOSFET, or we can say the p MOSFET. Okay, here we need to remember the, okay, the sign of the VT naught threshold voltage, it will be the negative. Okay, now we are going to see our next topic here, This will be the difference step involved with p-type substrate. Okay, different step. Different step involved with p-type. Right. Different step involved with p-type substrate, or we can say this for the NMOS, right, or N channel. So here, what we are going to do, let me first take the copy of this at 5 times. So here we are going to see what happened when we are, okay, in what happened when we are changing the gate to the source voltage. Okay, when we are changing it from negative to the positive, we are going to see this here, right? So this is the different step, okay, involved with the p-type substrate. Our next topic is this. So here what we are doing, we are making the connection like this. We are, okay, making this, we are connecting this source with a body, okay, and we are making this ground. Now what we are doing, we are making this drain to the ground. Now what we are doing, we are applying here, okay, the voltage, right? We are applying here the voltage VGS. Right. So in our first case here, in our first case, what we have make VGS will be equal to 0. So when this VGS will be equal to 0, means we have grounded this VGS, we have grounded this gate. Now here the source is connected to the body and is grounded, the drain is grounded, and the gate is also grounded. And we have seen in our first case is when the gate to source voltage is 0 and the drain to source voltage is 0, okay, then and the source is connected with the substrate. In this case only the depletion region is exist, okay, the depletion region is exist like this, okay, it will be exist like depletion region will be exist, okay. And when we have seen that also when a n type and the p type, okay, semiconductor come in contact with each other, what happened here, here the positive ion will be available, this is the immobile ion, here negative ion will be available, the immobile, right. Okay, so here we have having the two capacitor, here we are having the two capacitor, okay, right, like this is the gate oxide capacitor, and this is the depletion region capacitance, like this. So here we can say this is the gate oxide capacitance and this is the depletion capacitance. Okay, so as we know that what with the gate oxide capacitance, CO will be equal to the epsilon or x, okay, into area W, okay, L divided by TOX. What is this W? This is the width of the channel. We are seeing here, what is this W? This is the width of the channel. Let's see here. This is the width of the channel, right? What is the width of the channel? This is W dash will be the width of the channel. Okay, this one is W. Okay, this one we are saying this one as this, right? W. This is the width of the channel, this is the length of the channel, this is the thickness of the channel. Okay, so here the CO, gate oxide capacitance. Okay, this is the gate oxide capacitance, and this will be equal to the epsilon OX, okay, into W into L. This is the area, right? And this is the TOX, thickness of the this silicon dioxide, right? And what is the CD? CD is the depletion capacitance. Depletion capacitance, and it will be equal to the epsilon SI. This is the permittivity of the silicon into W. This W is nothing but the depth of the depletion region, this W, right? And L is nothing but the length of the channel divided by this will not the W, this will be the W, right? Divided by the W, the width of the, this is the width, okay, the width of the depletion region. This will be the thickness or the width of the depletion region, right? So, and this is again the width of the channel, okay, width of the channel, right? So here we have seen there the two type of the capacitance, the gate oxide capacitance and the depletion capacitance, okay. And the gate oxide capacitance is CO will be equal to the epsilon OX, okay, WL divided by TOX, and here CD will be equal to the epsilon SI, okay, and WL upon me, and this we can say this depth will be equal to the D, okay. Let us write D. Let me write D here. This will be equal to the D, right? So since the depth of the since the width of the, or we can say the thickness of the depletion region D, the thickness of the depletion region D is maximum in this case, okay, when the VGS will be equal to 0, and hence we can say when the D will be increasing, we are writing here CD will be equal to the depletion capacitance epsilon SI WL, okay, divided by D. And when this D is increasing, okay, in the depletion region, this CD will be decreasing, and hence we can say this as a this CD minimum, okay, this is the minimum depletion region capacitance. So we are writing here the CD minimum, okay. And since these two are coming in the series, we can write the net equivalent capacitance will be equal to CO into CD minimum divided by CO plus CD right? And we can say this as a C minimum, because here the CD minimum is here, right? Hence, and this, since this is the series connection, and hence the net capacitance, equivalent capacitance will be less than the minimum capacitance, right? So we are here, we have seen the three different things. For the first one, when the gate to source voltage is grounded, okay, or when the gate voltage is grounded, or we can say when the gate to source voltage is 0 and the drain is also grounded and the body is connected with the source and it is also grounded. So in this region, the depletion region and the depletion layer, okay, the depletion layer will exist, okay, near the SiO2 interface, okay. The depletion region exists near the SiO2 interface, having the width or depth d, and this is called the depletion region or the depletion capacitance, and that will be equal to the epsilon Si into WL divided by d, right, where d is the thickness of the this depletion region. And we can also say that the gate oxide capacitance, this capacitance is always available, right? The gate oxide capacitance is always available, and CO will be equal to the epsilon Ox, okay, W into L divided by TOX, and this TOX is the thickness of the this SiO2. This is also this W. This W is nothing but the width of the channel, right? Okay, now what we are doing, we are decreasing the gate voltage, okay, we are decreasing the gate voltage. This means we are applying the negative voltage at the gate terminal. So see here we are applying the negative voltage, right? Here we are applying the Vg is negative, okay. So when we have made the Vg negative by a small value, right? So what happened here earlier, this is having the positive ion, immobile ion, it has negative, right, in the depletion region, okay. Negative immobile ion will be present here. Now when we decrease the gate voltage by the small amount, okay, by the small amount, or we apply the negative voltage on the gate, okay, this negative, since this is the polysilicon gate or this is the metal gate, this negative voltage will be here, and because of that the charge polarization take place in the SiO2 silicon dioxide, because this is the dielectric, right? So here this will be the positive, this upper surface, this will be the negative, and since the negative charge is present here at the SiO2 interface, and it will be attract the whole, it will be attract, since it's a negative, and it will attract the positive charge. That's why it's attracting the hole, okay, hole from the p-type substrate. Since the p-type substrate has the majority of the hole, easily it will be available here, okay, hole will be available here. And right now what we are doing, we are decreasing the gate voltage again, okay, and we are applying the gate voltage negative by very large amount, right? So this negative voltage will come here, okay, right, this will be the positive and this will be the negative, and this due to the more negative voltage is applied at the gate, okay, the more hole will be attract, the more hole will be attract from the substrate, and this large number of the hole is accumulated in between the drain and the source. Large number of the hole is, okay, accumulated between the source and the drain, right? Okay, and hence in this region, okay, in this region the capacitance will be formed like this. This is the CO, gate oxide capacitance, and here because the depletion region is not here. Okay, the depletion region is not from here, and due to that, okay, no depletion capacitance will be here. No depletion capacitance will be here, only the oxide capacitance, right? And in this case, this is the CO oxide capacitance, gate oxide capacitance, and this is the depletion capacitance, right? This is the depletion capacitance. So this is the gate oxide capacitance, and this is the depletion capacitance, right? So what happened here, when we are applying the gate voltage by the small negative voltage, okay, by the negative voltage, okay, charge polarization happened in the SiO2, okay, silicon dioxide, because it is a good dielectric, and hence large number of the large number of the okay, large number of the hole will be attracted from the p-type substrate, okay, and it will be present between the source and the drain. When we are making this gate voltage more negative, then the large number of the hole is getting accumulated in between the source and the drain, okay, in the p-type substrate, right? Now what we are going to see, first we have make this VGS will be equal to 0, this VG will be equal to 0. Now we are decreasing the gate voltage, right? Gate voltage. Now we are, this will be the case, this will be the case 1, right? Or we can say here, let me see here, this will be the case 2, this will be the case 3. Now we are seeing the case 4, where we are applying the positive voltage, we are applying positive voltage by a small amount in the at the gate, okay. So since this is the polysilicon or the metal gate, okay, here positive will be there and charge polarization take place here, and because of the positive applied voltage at the gate, okay, this positive voltage, okay, will attract the electron from the channel, okay, it attract the electron from the p-type substrate, not channel, it will attract the electron from the p-type substrate, right? And the electron will be appear here, and the immobile negative ion is also appear here, immobile negative ion, or we can say depletion will appear here, right? And some electron is also present here. Now here the capacitance will be equal to the, this is the set capacitance, and this is the, this is COX, this one COX, this one, okay, this is the COX, and this is the CD, right? Depletion capacitance, because the depletion, okay, the immobile charge is present here, the depletion region charge is present here, and there will be the some thickness of this depletion region, and that's why the CD is present here, okay, depletion capacitance is present here. Now when we apply the more and the more positive voltage at the gate, okay, at the gate terminal, now when we have made this VG more positive, okay, more positive, okay, the more and the more positive charge present here, because of the charge polarization, the more and the more positive charge is present here, and due to this the more number of the electron is, okay, attracted, the more number of the electrons are attracted near the source and the drain, okay, or between the source and the drain, more number of the electron are attracted, okay, or accumulated, okay, between the source and the drain, between the source and drain. And where this electron, where is it's coming from? It's coming from the p type substrate, right? And here the capacitance will be, right here the capacitance will be, this is the CO oxide capacitance and this is the depletion capacitance. And in the depletion region is not present here, this depletion capacitance will be not here, only the oxide capacitance will be present here, this is CO, right? Now we are going to see the, we are going to name this difference region. Since this is the gate voltage will be equal to 0 and only the depleted region is present near the SiO2 interface, so this region is known as the depletion region. Depletion region, right? In depletion region the capacitance will be equal to the G minimum, right? And here we are applying the negative gate voltage by a very small amount negative gate voltage, hence the hole is getting attracted, the hole is getting attracted between the source and the drain, and also the immobile negative charge is present here between the source and the drain, and this is called as the weak accumulation. Weak accumulation, okay? When we are applying the negative voltage at the gate of very large negative voltage, okay, then large number of the hole is present here, and only the hole is present between the source and the drain, no immobile ion is present, okay, and this is called as the strong accumulation region. This is called as the strong accumulation region, right? Now when we are applying the gate voltage with the positive, okay, small voltage, right, the electron is getting attracted here, and the less number of the electron is present between the source and the drain, and the immobile charge ion is also present here, immobile ion negative ion is also present here. This is called as the weak inversion, weak inversion region, or we can say this is the weak inversion, right? And when we are increasing the gate voltage, okay, gate voltage, and this gate voltage will be more and it will be greater than the Vt naught, will be greater than the threshold voltage, then the large number of the electron is present between the source and the drain, hence we say that the region near the SiO2 interface between the source and the drain is getting inverted, okay, and hence this region is known as the strong inversion region. Strong inversion. So when we are applying the negative voltage, when we are not applying any voltage, then this will be the depletion region. Here the capacitance will be minimum, and this will be equal to C naught CD minimum upon C naught plus CD minimum, right? When we are applying the negative gate voltage, very small, okay, very small amount, hence the negative ion, okay, the immobile negative ion as well as the hole is present between the source and the drain, and this region of operation is known as the weak accumulation. When we are applying this gate voltage, okay, by a very large negative gate voltage, okay, when we are applying a very large negative gate voltage, okay, then the hole, only the hole is present between the source and the drain, and this region is called as the strong accumulation. Now when we are applying the positive small gate voltage, okay, then the electron as well as the negative immobile charge, okay, or negative immobile ion present between the source and drain, and this region is known as the weak inversion region. And when we are applying the more positive gate voltage, then only the electron is present in between the source and drain, and the region, okay, near the SiO2 interface is inverted, and this is known as the inversion occur. This is known as the strong inversion, right? So there is a local language to understand this, okay. Since this is the p type, okay, since it is the p type substrate, okay, it is the p type substrate, and what is accumulating here, okay, this is the p type substrate, and what is coming here, the hole. Okay, the hole. The p-type substrate is here and the hole is coming in between the source and the drain, hence it is known as the accumulation. ये घर किसका है? होल का। और आ कौन रहा है? होल। ये घर है होल का और आ रहा है होल एक्यूमुलेट होने के लिए, इसको हम लोग देन एक्यूमुलेशन बोलेंगे। ये घर किसका है? होल का। ओके, ये घर किसका है? पी टाइप का, होल का। ओके, होल पी टाइप में मेजॉरिटी चार्ज कैरियर होल होते हैं और माइनॉरिटी चार्ज कैरियर इलेक्ट्रॉन होते हैं। तो ये घर किसका है? होल का। और आर कौन रहा है यहाँ पे? होल। ओके, होल। Hence, it is known as, and since the large number of hole is present here, this is known as the strong accumulation. Now, see, this is the p-type substrate, and here आ कौन रहा है? The electron is coming right here. The electron is coming. Hence, this is known as the inversion. घर किसका है? होल का। आ कौन रहा है? इलेक्ट्रॉन। ओके, दिस इज नोन एज द इन्वर्जन। ये घर किसका है? होल का है। कौन रहा है? इलेक्ट्रॉन। दिस इज ऑल्सो नोन एज द inversion or the strong inversion, right? So this is the small trick to learn or to remember this. Okay, always see which type of substrate. Okay, this is the p type substrate, this is the n type substrate. What is coming here? If the opposite is coming, then the accumulation. If the opposite is coming, then the inversion, and if the same is coming, then the accumulation, right? So this is the p-type substrate and the electron is coming, then inversion. When the p-type substrate and the hole is coming, then accumulation, right? When the n-type substrate and the hole is coming, then inversion. And when the n-type substrate and the electron is coming, then accumulation, right? Okay, now we are going to see the this capacitance and this gate voltage diagram. So here we have seen in the depletion region this capacitance is minimum. Okay, this capacitance is minimum and this will be equal to the C naught into CD minimum upon C naught plus CD minimum, and this C naught is nothing but the gate oxide, and this is the depletion capacitance. And we have seen the formula here for the these two type of the capacitance. Okay, and in when we are applying Vg by a small amount, this capacitance exists here. Okay, depletion capacitance as well as the gate oxide capacitance. When we are applying the large negative voltage at the drain, in only the gate capacitance present and the depletion capacitance is not present here because there is no depletion charge in between the source and the drain. Now when we are applying the positive voltage at the gate by a very small amount, the negative charge ion, the depletion, this is known as the depletion region, is also present, and some electron is also present in between the source and the drain, and hence here the oxide capacitance, that is will be equal to the CO, gate oxide capacitance, as well as the depletion capacitance is present here. Same way, when we are increasing the gate voltage by a very large amount, that will be the positive gate voltage, then here there is no depletion region is exist, and hence the depletion capacitance is not present here, only the gate oxide capacitance is present here, right? Now we are going to draw the curve. Okay, so here we can say here the Vg will be equal to 0, and we can say this is the depletion region because here the capacitance is minimum. Here the capacitance is minimum, right? And since here the capacitance is maximum, okay, and here we are applying the negative gate voltage, right? And here we are applying the positive gate voltage. So for positive gate voltage, okay, this is the strong inversion because here we are applying the positive gate voltage. This is the weak inversion. This is the depletion region. This is again the weak accumulation. And this is the strong accumulation, right? वाई अकुमुलेशन बिकॉज घर किसका है, होल का। आ कौन रहा है, होल। देन अकुमुलेशन, घर किसका है, इलेक्ट्रॉन का। एंड आ कौन रहा, घर किसका है, पी टाइप, ओके, होल का। एंड आ कौन रहा है, इलेक्ट्रॉन। when the opposite occur then the inversion occur, right? Okay, so we can see this is the depletion region, or this is the strong accumulation and this is the strong inversion here, right? Now, and we can say that this is the low frequency, this will be the low frequency CVG characteristics curve. Okay, when we are increasing the frequency, this means when we are increasing the frequency, this means we are going the we are applying the positive voltage immediately, and then we are applying the negative voltage immediately, right? When we are going for the high frequency means from 0 to negative, and from, okay, from 0 to negative and from negative to positive, we are applying very fast from negative to positive, from positive to negative, okay. And because very fast, very quickly we are changing the gate voltage from negative to positive or from positive to negative, okay. Then when this will be the p-type substrate, the hole will become easily because the p-type substrate having the majority charge carrier as a whole and electron as a minority charge carrier, right? So for the p-type substrate, the hole is coming easily, but for the p-type substrate here, the electron is not coming easily because the electron have to break and make the covalent bond, okay, to come here, okay. It will have to break the covalent bond, okay, in the p-type substrate to become free and to come here. So when we are increasing the frequency, or we can say when we are changing the gate voltage more frequently, okay, more fastly from positive to the negative, then if the substrate is p-type, then the hole is coming easily because it has the majority of the hole as a charge carrier, but the electron is very less. If the large number of electron have to present here, then that electron have to break the bond and come here, okay. And because of this process, the electron will come slowly in between the source and the drain, and the hole will come fastly in between the source and the drain. And hence we can say when we are increasing the frequency, the inversion will not occur, only the strong accumulation and weak accumulation and depletion will be occur. So for the high frequency, the graph will be like this, okay. For the high frequency, we can say the inversion will not occur because for the p-type substrate, okay, for the p-type substrate, the hole will come easily because the hole are the majority charge carrier in the p-type substrate, but the electron will not come easily because to form or to make the large number of the electron, the large number of the covalent bond will be break, and hence large number of the electron will be present there, and hence we can say this is the high frequency. This is the high frequency C into VGS curve, and this is the low frequency CVG curve, right? And what is this? Is the C minimum equal to the CO into CD, form CO plus CD, okay. This CO will be equal to the epsilon OX W into L divided by, okay, COX, and this CD will be equal to the, okay, epsilon of SI W into L divided by D, right? D will be the thickness of the depletion region, okay. Now this is for the NMOS, okay. This is for the NMOS or N channel MOSFET or P type MOSFET, and what we are making, this is for the PMOS, and for PMOS, okay, this will be the Vg will be equal to 0, and when we are applying the negative Vg, okay, and we are applying the negative Vg for the PMOS, here the substrate will be the N type, okay, and here when we are applying the positive voltage, here the negative gate voltage and here the positive gate voltage, now then here the strong inversion will be occur, here the weak inversion, here the weak accumulation, this is the accumulation, and this is the depletion. Because for the PMOS, okay, the substrate is N, okay, for the PMOS the substrate is N type. So when we apply the negative potential at the gate, okay, the negative potential at the gate, right, the electron will become near the SiO2 interface or in between the silicon, in between the source and the drain, and since this is the sorry, for the p-type MOSFET, okay, the substrate is the N type, okay, and when we are applying the negative voltage, let's make a small PMOS here, okay, let's make a small PMOS with the PMOS, this is the P plus, with the P plus, okay, this is the SiO2 silicon dioxide, this is the polysilicon gate, and here we are applying the gate terminal, here we are applying the source, and here we are applying the drain, and this is the substrate, right. So when we apply the Vg will be equal to negative, then here the negative will be present, and hence the large number of the hole will be come here, okay, and since this is the N-type substrate and hole is okay accumulating in between the source and drain, so we can say this is the inversion, this is the inversion. Similarly, when you apply the positive gate voltage for the PMOS, the whole the electron will be present here, and since this is the N-type substrate and the electron is presenting here, we can say this is the strong accumulation region. So always remember, घर किसका है, इलेक्ट्रॉन का, आ कौन रहा है, होल, then it will be the inversion, and घर किसका है, इलेक्ट्रॉन का, आर का, आ कौन रहा है, इलेक्ट्रॉन, then it will be the accumulation, right, accumulation. So and here the low frequency, this is the low frequency, okay. What will be the high frequency graph, okay, what will be the high frequency graph, the high frequency graph will be like this will be the high frequency inversion is not occur, and for the low frequency inversion will occur, right. So here, okay, here for the negative, here is the negative VGS, okay, here is negative VGS, here is positive VGS, here is positive VGS, and here is negative VGS. Now, remember this curve, okay, because here the curve is really very important, and here we can see that the capacitance, okay, the capacitance of the MOSFET is changing with respect to the gate voltage, okay. Here we can see, we are seeing that the capacitance of the MOSFET is changing with respect to the gate voltage, so we can also say the MOSFET is a voltage control capacitor, voltage control capacitor. From here we can say The MOSFET is work as a or behave like a voltage controlled capacitor, because here the capacitor of the MOSFET is changing when we are changing the gate voltage. So we can say the MOSFET is a voltage controlled capacitor. Its capacitance is changing when the gate voltage is changing, right? Okay, now let's see the this Cocd formula. Okay, so this CO is nothing but the gate oxide capacitance. Gate oxide capacitance. So gate oxide capacitance is CO and will be equal to the epsilon OX, okay, into WL. This is the width of the channel, this is the length of the channel, divided by TOX. This is the thickness of the SiO2, right? And now this is gate side capacitance per unit area, okay, per unit area, and this will be called as COX. This is the gate oxide capacitance per unit area, and COX will be equal to the epsilon OX, okay, and not WL. Here we will not WL, because this COX is the CO divided by W and L, then hence COX divide epsilon OX divided by TOX, and it will be equal to CO divided by WL, and this WL nothing but the area, okay. So this is the gate oxide capacitance, okay, CO, and COX is the gate oxide capacitance per unit area, right? Let me highlight this. So okay, this is the gate oxide capacitance per unit area. This is the right. Now see what is the depletion capacity. Depletion capacitance is CD will be equal to the epsilon Si, okay, epsilon Si. This is the permittivity of the silicon, this is the permittivity of the SiO2, okay. So this is the epsilon Si WL divided by T. This is the thickness of the depletion region. Now depletion capacitance okay, per unit area will be equal to the epsilon A divided by D, okay, and this will be equal to the C shape, okay, right. So here we have seen the C minimum, okay, the C minimum will be equal to the CO into CD divided by CO plus CD. We can also write this as the C minimum will be equal to the, okay, COX into C dip divided by COX plus C dip, okay. Right, and this what will be the maximum capacitance. We can see here the maximum capacitance is nothing but the CO, the maximum capacitance is nothing but the CO, right? So the maximum capacitance is nothing but the CO here in the strong accumulation region as well as in the strong inversion region. The only the gate oxide capacitance will be exist, the depletion capacitance will not exist, and hence the maximum capacitance is nothing but the COX or CO, okay. This is the maximum, this is the C maximum will be equal to the CO, or we can say this will be equal to the COX. So when we are using COX, we will use the C dip, okay. When we are using the CO, we will use the CD, okay, because for this we have to divide this by the W, right? So here we are going to see one more important things, right? Then C max upon may C min will be equal to the COX upon may C depth plus 1, right? COX upon may C depth plus 1 will be equal to the C maximum divided by C minimum. This is another important formula, and the large number of the question is asked by this formula, using this formula in the previous year in the gate. Okay, this C max, the maximum capacitance to the minimum capacitance, will be equal to the gate oxide capacitance to the depletion capacitance, okay, per unit area, both of course plus 1, right? Plus 1. Okay, so in this video we have seen, okay, the little bit about the channel length modulation, and we have also seen the resistance in the linear region, in the saturation region, and also we have seen the different steps for the p-type MOSFET, okay, p-type MOSFET, right? And we have seen this how the MOSFET is behaving as a voltage control capacitor, okay, right? And we have also seen the formula for the gate oxide capacitance and the gate oxide capacitance per unit area. Please remember this, because this is really very confusing, okay? You will confuse in the exam between the CO and the COX, and this is the depletion capacitance. This is the depletion capacitance, right? Okay, in the next, okay, video we are going to see that what is the ohmic contact, okay, and the rectifying contact, okay. What is the ohmic contact and the rectifying contact, we are going to see in the next classes. Let me tell, if we are going to connect the metal, okay, with any type of, okay, semiconductor, okay, then the connection between the metal and the semiconductor is acting as a ohmic contact or the rectifying contact, okay, ohmic contact or the rectifying contact. And tomorrow, in tomorrow video, okay, we are going to see what is this ohmic contact and the rectifying contact, right? So thank you for listening, okay, thank you so much.